Thanks for coming. This is talk about Presto cost-based optimizer. And I'm here with Martin from Facebook, and my name is Camille. I work for Starburst. Okay, so I'm just curious, like, who knows what Presto is already, or maybe is using it? Okay, majority of you do know. Okay, awesome. So I'll keep it super short. Presto is obviously a distributed SQL engine for all your kinds of different data, and you can deploy it anywhere: cloud, on-premises, virtual environment, and you can query anything. Yeah, it could be Hadoop, could be S3, or any other object store that's S3 compatible. Also SQL databases like SQL Server, MySQL, Postgres, NoSQL engines, Cassandra, Redis, Accumulo, and so on. And you can use any BI tool or visualization tool that speaks SQL. And those could be obviously your favorite tools, just Tableau, MicroStrategy, or newer open source alternatives such as Superset or things like Jupyter Notebook, for example. So it's very, very versatile. And the key highlights on Presto: ANSI SQL compatible, very easy for anybody to talk to Presto. You don't need to learn any custom syntax for standard SQL queries. It's really meant for interactive performance, low latency queries, and high concurrency. That was the design goal from the beginning for Hive, for Presto. And it's proven at scale. As I will discuss later, it's used at higher scale by a number of organizations. It's sort of introducing this concept and being designed from the beginning to separate compute and storage, right? So Presto does not come with the favorite way to store the data, and it can be kept in many different places, and you can also scale your compute layer, your SQL engine layer, independently of your storage layer, and you're not tied to your Hadoop infrastructure necessarily, which is pretty powerful, especially now when people are moving more and more towards the cloud or cloud-like environments when compute and storage are no longer co-located. You query data where it lives, so you don't need to do any ETL, which is great to get quick time to insight. It's completely agnostic to your Hadoop distribution or your cloud vendor. You can run it on any cloud, any Hadoop distro, or you can roll out your own thing, and that helps a lot with the flexibility of how Presto could be applied. It's obviously community-driven open source project under Apache license, hosted on GitHub. Just a quick recap of the project timeline. I was born 2012 at Facebook. So Martin was one of in this core team of few engineers who started this. It was a direct answer to a project called Hive, which was also born at Facebook 4 years later, and in response to the lack of interactiveness in Hive at that point. Was open source a year later, and the community grew over time. 2015, the team that I led at a company called Teradata joined the community and invested a bunch into sort of readiness for enterprises. And since then, we see booming adoption. And late last year, my team actually started a completely new company focused purely on Presto, and it's called Starburst Data. As I mentioned, it's a widely adopted project at this point, despite not being tied to any big data platform. So those are just some sample of users. You can find anybody here from big internet companies to telco, financial, retail, and anything in between. There's obviously a longer list. If you click on this website, Presto is available on most of the cloud, in most of the cloud environments, and and you can deploy it any way you want, which was very powerful for those users here. Some of those users are obviously people I work personally with to help them run this in production and support them if they need help with Presto. And even at this conference, if you got a chance to talk to guys at Netflix, on LinkedIn, on Comcast, they all are using Presto. And right before this talk, there was another talk by Uber about Presto and geospatial functionality. And Uber is one of the most prominent users in the community. I'm not going to go through all of those stats, just a sample of what people are doing with Presto. It runs at hundreds of nodes in production, running tens and hundreds of thousands of queries a day, and querying anything from ORC, Parquet, S3, Cassandra, and you feel free to go to any of those users and ask them for references because they are really happy Presto users. Okay, so now I will just turn over to Martin to sort of set the stage to discuss performance, and then I will be back to discuss the specific cost-based optimizations we've done recently. Go.
Right, so Presto is built for raw performance. We employ a bunch of techniques like columnar processing, vectorized processing. When processing a query, Presto generates bytecode, then it hands it off to the JVM, which can then further optimize it, turn it into machine code. Presto uses data structures in memory that play well with the garbage collector, play well with the JVM, to be able to process rows as fast as it can. It's actually known for being able to for its brute force speed. The thing is, it doesn't matter how fast you can process a row. At the end of the day, if you don't reduce the algorithmic complexity of the plans you're going to execute or the queries you're processing, you're not going to be able to get the potential improvements that you would be with a more optimal plan. So we are one of the things we have been doing as a collaboration with Starburst for the past year is enhancing the optimizer to be able to make better decisions at runtime that depend on the shape of the plan, on the estimated cost of the operations, and made it aware of how the data is laid out, how the data, the statistics about the data, and Camille is going to talk about that a bit more later. But before we do that, I want to point out that evolving the optimizer is a very challenging process. We have a very diverse workload, both inside Facebook and outside Facebook. We have thousands of users using Presto every day. We have thousands of regularly scheduled jobs that we can't just make changes that go and break them. So we have to be very careful how we make every change. We have a very fast changing code base and a lot of developers actively contributing to it. So any change that we make has to be done. It is really important to make it as incrementally and as gradually as possible. We can't do just a big bang swap of any major component. So it's a challenge about how to make fundamental changes and at the same time make them incremental. So we're going to talk a bit about that. And this is made even more challenging by the fact that when changing the optimizer, we're touching an internal APIs that have a very large surface area. It's the classes and components that have to do with how we represent plans, how we represent all the operations that the engine can do. The optimizers are there's a pretty rich set of optimizers, so any change has broad implications across the entire code base. So it's a challenge, and we're going to talk about how we stage some of those changes. So if we look at how we started, like this is back in 2012, and it lasted for a few years. The optimizers in Presto were made of it's very rigid visitor-based optimizers. So we have a plan structure represented by nodes that have a hierarchical relationship between them, and the optimizers used to be just a set of, say, 10 to 20 well-known transformations that what they did was they took the plan, they did a bunch of transformations, produced a new plan, and then went on to the next stage. Kind of similar to how a compiler would do with the multiple compilation phases. This has a bunch of problems, both in the fact that they are visitor-based, which means that the optimizers are responsible for applying the transformation as well as walking the plan tree and making decisions of how to walk the tree in what order, how to apply the transformation rules. So it's very rigid, and there's no way to leverage. There are some optimizers that may produce some transform plan that other optimizers would be able to leverage, and then those would produce something that the first optimizer might be able to leverage. And with this sequential serial execution of the transformations, it's impossible to do that. So there's no way to kind of iteratively improve the plan. So it's hard to add new optimizations because every optimizer has to implement all the visit methods for every single node. So you have to reason about how a given optimization has to deal with every possible node, even though the optimization may be irrelevant for that specific type of plan node. It's hard to add new operations or new capabilities to the engine. For example, if you wanted to add, well, we have sorting, but let's say we wanted to add sorting, it means that we had to add a new operation, and then we had to touch every optimizer to tell them how to deal with that node. So we have the opposite problem there. And then it's because they are monolithic, it's hard to test the optimizers. You have this big class that knows how to deal with every possible node, and the input is a plan and produces a plan. So you can't test how the optimizer behaves for every specific operation. So what we did is we turn it into, let me give you an example. So if we have a plan that looks like this, so let's say we're talking about predicate pushdown, the predicate pushdown optimizer takes this plan, does a bunch of processing, and returns that other plan. It's what happens inside is completely opaque, and it's a one-shot thing. So what we end up doing, this for the past couple of years, we turned the optimizer into a rule-based optimizer that deals with more granular transformation rules. Each rule has a pattern that it can match. So think of, we're doing predicate pushdown. So we can write a rule that says, I want to push a filter through a projection. So you have a filter on top of a projection, I want to push it down. So the pattern would be filter node with a source or input node that represents a projection. When the pattern matches, the optimizer can call the transformation rule saying, okay, apply the transformation to just that local part of the tree. And this is very important because it allows us to it gives us more flexibility. We can decouple the walking of the plant tree or the decision of which parts of the plant tree we focus on from the actual transformations that we want to apply. We can develop targeted transformations. They are easier to reason about, easier to test. So it's just generally much better. And this is not something like revolutionary. It's the way many other optimizers express how they can perform transformations. And so to give you an example for the same plan, what would happen in this case is we would have one rule that says push filter through aggregation. It would just do that transformation between filter over aggregation to aggregation over filter. Then the optimizer that is considering the rules and walking the tree says, okay, I match some other pattern, in this case filter over filter, for the merge filters rule, and then applies that and produces a merge filter. It's a local transformation that it gets spliced into the plan at that point. And then after further walking of the tree, may find another pattern that matches of pushing a pattern for the push filter through project, which also does a transformation. So you get the same result, but it's a more granular transformation at every single step. So now the question is, how do we go from one to the other, from the visitor-based to monolithic optimizer to rule-based optimizers? And the strategy we took here is to implement the optimizer that knows how to walk the tree and consider rules and match patterns as a monolithic optimizer that we just insert into the sequence of optimizers that we used to have before. And then we can do a migration of one at a time from the old style to the new style. So I mentioned before that we want to control risk. We want to control how we have a lot of existing workloads. We want to make sure that we don't break anything in terms of functionality, in terms of performance. So we have to be able to try a new change and easily back it out if there are problems without having to back out the entire code or undo or revert the commits or anything like that. So the strategy we took here is we extended that rule-based optimizer to take in this case, for example, we're trying to convert the limit pushdown into a set of rules. So we can tell the rule-based optimizer, here are the new rules, and here's the old optimizer that does exactly what these new rules do. And then we have a config option for the server and a runtime config that we can enable on a per query basis that allows us to fall back to the old behavior. So the idea is we roll out a new version with this transformation. We enable the new optimizer. If we see problems on specific queries, we just turn that option off and they fall back to the old behavior. If we see widespread problems, we can just turn it off for the entire cluster. Go fix the bugs, etc. And then after a few iterations, after we're comfortable with the code, make sure that it runs properly, we can remove that legacy behavior. And then all the plans will be processed just by the new rules for that specific part. And then over time, and we can do this incrementally, you can take one of the existing optimizers, migrate them to the new style of optimizers. And so this is what Camille is going to be focusing on, specifically the cost-based optimizer. So what we added over the past year or so is the ability for these rules to reason about cost. So we implement cost-aware, cost-based optimizers as regular rules that the framework that knows how to walk and evaluate patterns it can consider, and those rules can get fed with information about the cost of the shape of the data and the ability to evaluate the cost of different parts of the plan. And then they can do local decisions about in this case, for example, how to reorder joins based on the estimated cost. So this just appear as regular rules to a system. It's just that they can take into account cost in order to decide whether to make a transformation or not. Right.
Thanks, Martin. So let's dive into the cost-based optimizer, the first release of that. We call it V1. We are actually very, very happy about the results we are seeing here so far in this first version, and I will show you some benchmarks later. But we want to stress this is not the end. This is the beginning for us in terms of cost-based optimization. So in this first release, we have support for statistics that you have already collected in your Hive metastore. So we'll basically play nice in the ecosystem and leverage what's already there. We understand that most of the people already have statistics in their Hive metastore because they collected them with Hive and they use it across their ecosystem. So we'll leverage that. We'll do several things. First, the most important is to reorder joins from what the sort of natural order, syntactical order in your query. We'll reorder them based on our selectivity estimates and cost model. We'll reorder them so that the query execution is going to be faster. And then we'll also look at the types of joins, right? So Presto supports two kinds of joins. One is sort of the repartition distributed join that basically shuffles two tables, and there's also the broadcast join, which basically replicates a smaller table across all nodes, right? So we'll make that decision now automatically for you, rather than allow you to sort of tweak it via session property or config property. And then finally, we'll also make a determination for each join, which input should be on the left versus right side of the join. And as we realize in our careful benchmarking and experimentation, is that it actually makes a lot of difference sometimes, right? It's putting a smaller table on your inner side to build a hash table from is actually highly beneficial for the CPU. And Obviously, this talk is short, right? So we'll do the high-level overview of the optimizer. There's a ton of more details that we put on our blog, and you can go to starburstdata.com technical blog and read all the nitty-gritty details of how we sort of enumerate joins, how we make a decision for various types, and definitely encourage you to do that. So just diving into statistics and cost, Hive MetaStore today offers several things. It will tell us what's the number of rows in a table, and this is obviously on a table level and the partition level. And we can also learn what's the estimated number of distinct values for a column, how many of them are sort of null values, versus non-null values, what's the minimum maximum value for a given column in a given table or partition, and average data size. Right? So this seems pretty basic, and obviously if you read database literature and commercial databases offer a ton of more complex statistics, but even those are pretty good to start with, and they enable a bunch of optimizations, and it can result in a huge performance boost. So our cost model, we actually spend some time to think how we balance CPU, memory, and also network I/O, and so the cost model includes all those three, and makes sort of a balanced decision to sort of get you good performance, but also reflect the fact, the relative cost of those different factors. Okay, so the most basic optimization I mentioned, which is decide, can we make a better join type selection, right? So if you happen to join two tables and one of them is very small table, instead of reshuffling both of those based on the join key and sort of create lots of network I/O to send this data across nodes to bring the corresponding rows into a single machine to perform a join, we can actually just distribute the small table to all the nodes, right? And depending on how small is the table, how large is the cluster, and what's the cost of sending this data over the network versus reshuffling everything, we make a call, okay, maybe we just switch to a broadcast join. And so Presto can do that now by just setting the property, but this decision will be made now based on the stats and the cost. And what's more, in your complex SQL query, you may have 10 joins, right? You're joining 11 tables, you have 10 join operations. This decision will be made for each single one independently, right? So you may have actually a series of broadcast joins followed by some distributed repetition joins, and then again maybe there will be some broadcast joins at the end that are sort of joining some dimension tables to the end result, right? And that's a big step forward, because with sort of the pre-existing property, you could only decide that for all the joins at the same time, and that obviously it was suboptimal in many cases. So that's pretty basic. The second thing is there's sort of decision on the left or right side, and here let's say both tables are bigger, so that there's no way to do a broadcast join, but we still can make a decision. One of them is smaller than the other one, so let's put it on the inner side, and then probe with the rows coming from the larger table. Let's probe that hash table built off the smaller table, and that improves CPU significantly. That was the second optimization. The most interesting one is obviously the join reordering, right? So let's say you have this classic example of customer orders and line items. Today, you can basically write a SQL statement that has those three tables in arbitrary order, right? And based on the statistics, Presto will make a determination, right? It probably makes more sense to join two smaller tables first, and before joining the large one at the end, right? And so that's a simple decision to make, right, based on statistics and a cost model. So we're making this decision, and we have this plan here on the left, right? But now we look again at this plan and say, okay, well, so we still need to want to sort of change the shape of this plan, because we want to put the output of the orders and customer join on the inner side of the subsequent join, so that the line item, which was the largest table, was actually on the outside, and it will be probing into the hash table built of the result of the first join, right? So we make this jump into the right side of this on this picture, right? So all those things are working sort of at the same time and are applied as a whole of the three major changes we are making. So we made this determination. Yes, line item is the largest table, so we'll join it last. Great, right? But what if there are filters, which is usually the case in your SQL statements, right? So it turns out that your large table may become actually pretty small if you have selected filters on that, and that completely changes the whole decision process, right? Because line item is now much smaller. It's actually the smallest of all the three relations that are taking part in this join, in this query. So we'll actually join it first, and we cannot join it with the second smallest table, because there is no join key that will allow us to join the customer with line item directly. So we need to fall back to join line item with orders, because the output of that join is going to be very small, right? So it makes sense to do it first, and then join with the customer table later. And this is how we sort of move that whole thing into the right side with the edit filter. And this is possible because we estimate filter selectivity, and we also estimate all the join selectivities as well. But just for sort of interest of time, we'll discuss some elements how we propagate statistics through the query plan, right? So we obviously start with a basic base table statistics. So all those three tables, they have that many rows, as you can see. Then for each column, we know roughly the number of distinct values, and now we apply a filter. So what happens, right? So in the first case, filter is pretty simple. It asks for all items that are larger than 0. From the min-max values in the Hive metastore, we know that basically every single row will pass that predicate. So basically the cardinality of a table is still 61 million rows. But we didn't know that there are, we couldn't know are there nulls there or not. Maybe that statistic is missing, right? We have no idea, right? We had no idea. There was no statistic was not collected. For example, was a gap in stats. But because of this filter, we can actually now say for sure there will be no null values after this filter, right? Because that just counts for relational algebra, right? So we make that this information available for the subsequent steps in the plan, and we can make use of this information. For the second case, we have a filter, and we're just asking for a specific line item with this number. So because we know how many of different unique values for item are there in a table, we can make a determination that, assume there's no skew, right? For simplicity, we expect only 3,000 rows coming out of this table after application of that filter, right? And what's more, we used to have a bunch of unique values, but now we'll have only one unique value for that specific column. So we update this statistic, and we propagate it next to the subsequent phases of the plan. So when we make a join determination, as I was showing on the previous slide, we can now know for sure there will be on one NDV value, and when we join with another table, that will be impacting the subsequent results. And very similar example below, when we have two values, that obviously is two NDVs and 6,000 of rows. Okay, and so to do the whole join reordering and decision processes, we applied join enumeration algorithm and the costing of each possible combination of tables. And we support now both left deep joins and bushy joins. The algorithm itself is pretty involved, so I will not cover it here. It's actually described in detail on our blog, so please go ahead and read that if you are interested. Just to sort of give you a flavor, it's based on a dynamic programming, and we are doing sort of the top-down traversal of the possible join combinations, and we cost them as we go. We sort of memorize the combination of each join and the cost we computed, so that we don't have to repeat that computation for every branch of the algorithm. And at the end, we have all the combinations costed, and we make a determination among all the options. This is the one that that works best, at least based on the stats. What we in the cost model, we determine this join is going to be behaving very well. At the very least, it's not going to be a disaster, right? Because this is something you also want to avoid, disastrous plan. So now with all of these optimizations, you're probably curious, okay, what we actually achieved. So we run a lot of benchmarks to understand the impact of the optimizer. One of those benchmarks, which is pretty standard, is TPC-DS. It consists of 99 queries. So as you can imagine, going through all of them, every single is a lot of work, and we did a lot of iterations to improve our costing mechanism and join enumeration to achieve good results. What I'm showing here is a subset of the queries that performed best among that 99 queries. We saw no regressions among all the 99 queries that we ran, so which was good, right? Optimizer is not making bad decisions. That's very important. And among those 99, around 20% is above 5 or more speed up, 5x or more speed up. And I think the largest speed up we observed on this particular cluster, which was on-premises cluster, was 14x, I believe. And again, there's a URL at the bottom. You can read the full sort of report on how we run the benchmarks, what is the configuration, hardware, and so on, and exact breakdown of the numbers. And what we're testing here is basically Presto versus Presto with optimizer on and off, right? So I just want to make that clear. One good thing is, you probably heard in the past that Presto is unable to run all the TPC-DS queries. This is no longer true with the optimizer, because we are making good decisions in terms of performance and also good decisions in terms of memory consumption. And most of the queries will now complete on with much smaller memory requirements. Presto is able to run all of those at reasonable scale. And so we're really proud of this achievement. So this was on one cluster, one benchmark. The other benchmark that we recently ran, that was run on AWS. Again, Presto with this optimizer integrated, and Presto without this optimizer integrated. And those are sort of the relative speedups for selected queries. At some point, we basically, after observing a bunch of numbers, we basically said, okay, this is good enough. We are basically confirming from optimizer it's making the right decisions. So we did not actually complete all the 99 queries. It was cost prohibitive when you turn off the optimizer, because it just takes so much time, and that obviously costs money. So we stopped. The good outcome of this was we can now see, for the slowest query in this, or so the smallest speed up in this query, it was already it was still 50% over the non-optimized query, which is a nice boost, right? And it can go up to 20x for one of those queries. And I think on average is above 11 times. So you have over an order of magnitude speed up for your Presto queries in the cloud, which obviously in the cloud, time is money, right? So because you're burning the CPU and instance time, so you're just putting more money if you're running unoptimized Presto. And if you want to try it now today, definitely go to the URL below, and you can see optimizer in action, and observe this on your workload, not the TPCDS, which might not be representative or similar to what you're running in production. So definitely encouraging you to do that. Okay, so now we took this from the artificial benchmarks into some realistic workload. This is actually coming from our friends at Facebook. Presto at Facebook is obviously highly tuned, is already performing at its peak, right? So our goal here was not to show a huge speed up, was make sure we are not making bad decisions, right? And we are not causing some performance regressions. So this is a subset of performance queries, of sort of subset of the benchmark that was representative of production queries at Facebook. And as you can see, those highly tuned, manually tuned queries, majority of them, we are basically on par with those manually tuned queries, which is really good. And we actually found some queries. Facebook found some queries that are running now faster with the optimizer versus humanly optimized query. So which is nice, right? And so, well, someone may say, well, this doesn't tell me I can save a lot. Well, I can always manually tune queries. While that's true, that also costs time and money, right? To hand tune every single query. If optimizer is doing a pretty good job most of the time, then you can sort of skip doing this manual step and tune every single query carefully, because you can trust optimizer majority of the time. And for less experienced users, you may actually get much better results out of the box without involving engineers to debug your query. So that was good. And as I said, well, this is not the end. For optimizer is the beginning. The project already took long time to get it to this point. We are comfortable releasing this to everyone. We're contributing this back to the open source, obviously, and running this regression testing at Facebook was part of it to make sure it's not going to impact the current users. And it's available in the cloud if you want, but we are pushing on this further. So what we want to do next is to introduce additional rewrites that we realized if we apply those rewrites, which are actually not cost-based themselves, we can actually transform the query plan into a form that will allow the join reordering rule to make even better impact, include more possibilities. And for example, part of the TPCH benchmarks is that there's like lots of complex nested subqueries and they look really ugly, and you need to basically unwind many of them to make it available for the join reordering rule to make the best possible decision. And we are doing some of this for our next release, which should be out in a few weeks. Also, we would like to cost and consider statistic propagation and estimation for more and more operators that we initially skipped because they were not sort of the most important ones. So we'll be doing this next. That will again allow us to make more careful costing and decision on more complex queries. We are considering building built-in statistics collection for Presto so that you can run analyze table in Presto rather than rely on Hive or other tools to collect stats during the sort of the transformation loading process. I think this will be very useful for users who don't have Hive in the picture anymore, which is increasing number, especially in the cloud. And also add connectors for additional statistics for additional connectors, right? So all that work that we've done so far is about statistics for Hive Metastore, which basically covers the major two data sources, HDFS and S3. But what if you have Cassandra tables or you have Postgres tables? in your mix, and Presto can query across all of them in one query, and say you have 5 tables coming from HDFS and 2 tables coming from different systems, you need statistics for those other tables to be able to do the global optimization across all those tables. So we are going to work on exposing those statistics as long as the data source we are talking to is able to provide us at these basic stats like number of rows and so on and so on. We'll be able to expose them and include in the overall cost optimization process. And then beyond that, obviously there are more complex stats we can work on. So histograms. You may notice that the basic Hive stats are not going to help you when you have skew in your data, right? For example, if someone is selecting this item XYZ that I was showing earlier, and that item is actually the most popular item in the table, and it actually is 40% of rows, we want to know that. Otherwise, we are making a wrong assumption. It's going to be sort of on average the same selectivity of the filter. Okay, and beyond CBO, there's a bunch of work in Presto itself. So we are enhancing spill-to-disk functionality in Presto, which already exists, but we want to make sure all more operators support that functionality. The engineers at Facebook and Uber are optimizing geospatial functions, and we had a great talk right before this one about geospatial functionality. New connectors, Elasticsearch, again built by Uber, Kudu. This is a community contribution as well. So more data sources are coming to Presto, and there are projects around the resource-aware query submission and overall performance improvements. There's always something you can improve in the execution engine, in the planning. So that's it. I have a bunch of links for you to follow up in the future. The slides will be obviously published after the conference. You can learn more about Presto. And this is it for the presentation today. Thanks again for coming, and we are open for questions. We can stay as long as we want. Thanks.
Go to Mike.
Hey.
Yeah.
I have a question. So in your cost-based optimizer, do you require all the tables to have the stats ready? So what if one table is missing some stats?
Mm-hmm. Right. So we definitely build the optimizer to be resilient to missing stats or incomplete stats. If your table has 0 stats, like there's not even a wild guess on how many rows there are in the table, it's impossible to make a smart decision, because that table might be just a tiny one or might be a huge one, the largest one, and you'll be putting that table in the wrong place in a join order. So at that point, we basically are, as a safety net, we basically bail out and say, the user is probably doing the right thing. We are not going to change the syntactic order of the query, because we have no idea what's going on in this. And we can make local decisions on individual joins, like is it broadcast or repartition, but we cannot change the whole global order of relations. Thank you. Good question.
I have 4 questions.
All right.
Is the CBO, is it in Starburst distribution of Presto, or is it available on GitHub for public consumption?
Okay, so right now the ready release that has everything integrated I discussed is in the Starburst distribution, which is free and open source. You can grab it and use it for free. No problem with that. And it's also on the AWS Marketplace. We are making all those contributions available to the main repo, and we do this gradually. We actually started 3 months ago, and we are moving everything. And I think the major pull request, the largest, that introduces this join reorder rule that will basically make the whole work complete, is under review by engineers at Facebook. And once sort of the code review is done and all the regression testing, it will be integrated as well. And our goal is to make everything open source here.
We expect that to be over the next few weeks.
Yep.
So say a month or so.
Okay.
Yeah.
Cool. The next question is the CBO. Let me forgot. I have 4 questions in between. How are they stored? Like, where are the stats? You mentioned they are stored in the Hive meta store. Like, does it mean like Hive has access to the Hive metastore directly it stores, or it stores through HCAT or something like that?
So this is the same shared Hive metastore everybody else is using. Hive, Spark, Presto, everybody else. The same stats, the same format that Hive collects stats in is available to Presto.
Okay.
So, but just to clarify, the engine doesn't store or doesn't deal with storing the stats. It leaves all those decisions to the connector, and then a connector can choose to store them. I don't know, in its own data store, in the metastore. In the case of the Hive connector that ships with Presto, that uses the open source Hive metastore.
Yeah.
In the case of the Hive connector we run at Facebook, we have a custom store for stats. We have a different implementation of the metastore, so we swap it out.
So one of the slides said built-in stats collection. That means will those be stored within the Hive, one of those like system connector, JDBC connector, or is it some other place we need to provide a MySQL or something to store it?
No, so the stats are managed and stored by the connector. With the built-in collection, they have two approaches. One is you can do it offline by running a command that will scan the tables, compute a bunch of statistics, and then tell the connector, here are the stats for the table. You deal with where you want to store them. The other approach is to do it online. You write as you write a query that writes into a table, Presto adds instrumentation to the query to gather the stats, and when the query completes, it provides them to the connector to say, for this table you just created, these are the stats, or as part of the creation of the table.
Right.
Okay.
And it's up to the connector to decide where to store them.
Sure.
Correct.
The ORC file format also has some kind of stats like min, max, number, and cardinality. So if you have that, do you still need these stats, and what is the benefit of like performance difference between ORC stats versus these stats?
Yeah, the ORC stats are good for runtime decisions like deciding to skip stripes or row groups, or basically things that the engine is going to consider when it's processing the actual data. During planning, looking at the org stats can be prohibitive. If you have, it's a problem if you have a table with lots of partitions, because the optimizer needs to look at all the partitions, get all the stats for all the partitions, and that incurs a cost during optimization. You don't want to spend too much time doing that. If we had to look at the files, then that might be looking at millions of files.
Right, it's suboptimal. Yeah. Without looking at the files, you can make the decisions. Got it. Thank you.
And latency, obviously, optimization is great if it turns out to be a good decision, but say you are not making a huge performance boost for this particular query, but you spent like a minute gathering stats, right? That's not going to be a good trade-off, especially for interactive workload that Presto is optimized for. So,
Cool.
thank you.
Can I use Presto in my Spark Java code?
Can you use Presto in your Spark Java code?
Yeah, my code is in Spark, Java Spark. Can I use Presto?
An interesting question. I believe Spark can talk to any JDBC data source. So that could potentially be Presto.
Spark can talk to Hive.
Hive or any JDBC, right?
Is that the same way when I use Presto versus not use Presto to access Hive table?
I think that should be possible, because this is essentially you'll be just issuing a SQL query via JDBC to Presto rather than Hive. So it should be possible without an issue. The question is like, what's the use case? Why would you use Presto versus Spark, right? And what we see from majority of big Presto users, they use Spark for ETL, for transformation, for machine learning, sort of non-latency sensitive workloads, while they use Presto for SQL, highly concurrent interactive SQL. And they basically use those two separately, reading off the same data of the same Hive metastore. And that way those two systems are sort of coexisting and serving different needs.
So one issue you're going to have today, if you have a Spark job that needs to talk to Presto, you're going to have to do it via JDBC. And that's going to be a single channel to talk to Presto. So Presto is going to run the query in parallel, but then all the data is going to stream through one JDBC connection. So that might be a problem depending on what you're doing. we are working on improvements to the client protocol for Presto to be able to support clients that can read data in parallel. And once we have that, we can have tighter integration between Spark and Presto. For example, Spark can say, I can tell Presto, I want to run this query, give me a bunch of different places where I can go and fetch data, and then Spark can schedule the individual Spark tasks with a connection to each of those data sources, so it can process the data that's produced by Presto in parallel, and you're not bottlenecked by one connection. Well, there's nothing out of the box right now, so.
Good question. See, I've seen the Presto has an architecture of coordinator and workers.
Yep.
So does these workers need a lot of memory to cache this data, or pull it into memory to process the data?
No, there's no caching in Presto. So the way Presto, so depending on the shape of the query, you might need more or less memory. For example, if you're doing just a scan from a table, apply a filter, and then write it back to some other table, there's almost no memory requirements other than for the input buffers, for the ORC readers or Parquet readers or whatever the reader is, for the buffers that exist between each of the workers as they talk to each other, and then for the writing, for the buffer for the file writers. But each of those is bounded in size. Like Presto doesn't hold on to all the data in flight. It will stream through the data through the system and write it. If you're doing aggregations, joins, order bys, window functions, you may need to keep more data around because of the nature of those operations.
Because the reason I ask this question is, like, I see Presto workers as containers in Tez. Like if you're running a Hive query on Tez or just a Hive query on MapReduce. So even there, the work is distributed among the containers. So I see the same here. So I was wondering how Presto gives much faster or better performance.
Than Hive, you mean?
Yeah.
Well, Hive uses MapReduce under the covers, which so MapReduce persists the data to disk after every single step of the mapper, before the reducer, and after the reducer. Presto doesn't do any of that. All the data streams from worker to worker without touching persistent storage. So that's one of the ways we get performance. Then, like I mentioned, there's vectorized processing, bytecode generation, which Hive, like Tez, and those systems have these days, but they didn't have like 6 years ago. So,
thank you.
So one question regarding Spark SQL. So have you guys done any comparison between Presto and Spark SQL in terms of performance or whatever other things? And do you see it as a direct competitor with Presto?
Could you also add Hive as another engine to compare? I mean, in addition to Spark SQL.
Okay, so the question is, can we compare performance of Presto today with the optimizer, with Spark SQL, Hive, and Impala, or all other things in the planet? And I'm sure people will do that, right? We wanted to stay away from this because I don't think I'm an expert of tuning Hive, and I heard it requires a bunch of tuning. And it's the same true for every other engine, right? So I'm not the expert in this. We compare Presto to Presto. That gives you sort of a relative performance, and I'm sure people now, after releasing all of this, will do all the cross comparison of the benchmarks. And I trust independent benchmarks more than being run by any vendor or someone who is obviously in favor of one specific project. Will definitely help tune Presto, whoever is running the cross comparison. But from the experience that all the Presto users and beyond, I'm seeing the clear pattern which I mentioned. Nobody's using Spark SQL for highly concurrent, low latency workloads. Nobody's using that. I haven't seen at least the case anywhere published, while Presto is optimized for that use case. But Spark SQL is awesome for data transformation, ETL, and sort of bigger jobs that are sort of less latency sensitive, do not require that much concurrency, and you don't have lots of BI users hitting the engine at the same time. So basically, somewhat different use cases. And then maybe there's some overlap, but it's not that important at this point.
So one thing is you can use the benchmarks as guidance, like TPCH, TPCDS, but at the end of the day, you have to run it on your own workloads, because your workload may not be or TPCH or TPCS may not be representative of your specific workload. So you're gonna have to see like how your queries perform on each of the engines to see if you get a benefit.
So the question is how how Presto compares to HBase. Well, HBase, first of all, HBase is a data store, so Presto is just a SQL engine. If you want to, and HBase is also sort of optimized for very low latency queries, but those are point queries. Like you want to fetch a user data for this particular user ID, right? Presto is for analytical queries that are looking across historical data and looking at the trends across the last week, last year, among the traffic generated by users. So completely different approach, right? I would see HBase could be one of the connectors for Presto, the same way Cassandra is, when Presto can talk to HBase to extract some information and correlate it with other data. But you know, HBase to Presto is essentially, those are not the same systems at all. So different use cases completely for those. We do not have currently HBase connector. I think there is some effort in the community to build one. SQL on HBase is somewhat solved problem by a project called Phoenix. I see someone from the Phoenix community here. So there is not such a pressing need to build a connector for HBase, but if someone in the community wants to do that, we are happy to help. Okay.
So my question is, if I don't, so right now our code is using Spark Java. If I don't, I want to utilize Presto, can I just call Presto from Java itself without Spark?
Yeah, because there's a JDBC driver for Presto, so you can make
just
a JDBC connection and execute query, correct. Yep, very simple, yep. Yeah, there's actually an example in our documentation how to do that, I believe, so.
Presto is just a SQL statement,
Yeah,
there are
it's
other
SQL
APIs?
Just SQL syntax, yeah.
Okay.
There are internal APIs, but you're probably not interested in those. So
SQL would be
yeah,
enough.
SQL via JDBC is the best for you.
Thank you.
Okay, all right.
So is Presto a fault tolerant? Like for example, if you are running a query and the worker node dies, what's going to happen with the query?
So today, if one node dies, I mean, because of what I was talking about, the data streams through the nodes, it's kept in memory, it's never persisted. If a node dies, any task associated with a query running on that node will fail, and the queries and those queries will fail. So it will affect any query that was running on that node. So now you have to look at what does it mean for a node to fail, and there are different kinds of failures. For example, a node just simply dying, like rebooting, or there's a hardware problem and all that. That's not the common kind of problem we see in production. We run thousands of nodes across multiple clusters, and like nodes disappearing or crashing or having hardware failures is not, that doesn't happen very often. So that's not the major concern. There are other classes of problems, like for example, I know because of inadequate tuning, you end up with garbage collection that takes a long time, and the node becomes unresponsive, and then the rest of the cluster thinks the node is failed, and so on. In those cases, yeah, you'll see queries failing. That can happen more often. You can work around most of those by tuning your memory settings, your GC settings, your concurrency, and so on. Now, having said that, we are planning for over the next half to start working on adding some fault tolerance, more granular fault tolerance to the engine itself, to be able to recover selectively when some part of the query fails. Sorry, the idea would be to selectively checkpoint or persist state for the query, so that when some part of the query fails, we can recover from that stage, as opposed to having to rerun the entire query.
Okay. Another question I have, because we were evaluating like different products actually, and this is one of the challenges we had. What is the cluster size actually that we are running in Facebook or the Presto actually? I just want to understand like whether it can scale like to the thousands of nodes of cluster that you mentioned actually.
Well, we run multiple clusters, but any given cluster is anywhere from 100 nodes to 800 or 900 nodes. And then we are actively working on being able to run single clusters that are bigger than that.
Okay, and those are like analytical workload that you put on actually plus Presto?
Yeah.
Okay, I don't see any more questions. Thanks so much for coming. As we